Okay, so the topic of today's presentation is energy performance evaluation and benchmarking of commercial buildings in India. My name is Saket and I've been working on this project for a couple of years now. The main motivation behind this presentation is to answer the question, how do we know if our buildings are efficient? So we have been designing and constructing and getting rated buildings which are so-called efficient, but how do we know that they are actually efficient and are being operated efficiently? So as I said, the intention that all of us share is designing of efficient buildings. And in a typical process, we design, construct, and then get an as-built building which is designed or constructed to be efficient. And at that stage, we get it rated and we say we have an efficient building or a green building. If you empirically look at some data, and this slide is from USGBC, US Green Building Council, all the rated buildings claimed or had the intention of savings, projected savings of about 25% above the baseline, which is in the left side. So the proposed savings were 25% on an average over the baseline. But when the buildings were constructed and their performance was measured, on an average they were still saving around 28%, which was slightly better than what they had projected. But there were clearly a lot of buildings which were actually consuming much more energy than the projected savings, and few were definitely consuming much less energy. So going from a proposed phase to the actual phase, we see that there is a huge disparity. Buildings can actually be more efficient or be less efficient than what the original intention was. So all of us have this expectation that our building would be efficient or is being operated efficiently, but when you start measuring the performance, it can be either ways. And it's not that somebody is trying to game the system. There are a lot of things which can go wrong, and they can happen at the design stage, simulation stage, material specification, execution, field conditions might change, the use pattern might change. So there is always a big gap between the intention and the outcome, and it's often very difficult to pinpoint why this gap is. And unless you can say that this is the reason for this gap between the intention and the outcome, it's very difficult to address it through retrofit or change in operation conditions or any other intervention. So going back to our efficiency cycle, once you have the building ready, which is so-called efficient or is designed to be constructed efficiently, it goes into the operation phase. And once the operation starts, then we can actually do some evaluation and comparison and say, okay, now this building is operating efficiently. This is where the measurement and the comparison part comes in. And at this stage, using actual data, you can make a robust claim about the efficiency of your building. So I'll take a minute here to explain what are the issues in evaluating and comparing performance, which will drive the rest of the presentation. So suppose we want to evaluate the performance of our building, and let us take the analogy of an apple. So suppose we say that the performance of an apple is determined by its size, and in case of our energy efficiency we say kilowatt hour per meter square per year. So suppose in this case we want to measure the performance of this apple and say the larger the apple, the better it is. Just by measuring the apple's diameter, we still cannot say whether it's a big apple or a small apple. We need to compare it with other apples and then say this particular apple is better or larger or worse or smaller. Similarly for buildings, when we measure the kilowatt hour per meter square per year, we need to compare it with other buildings to say whether this is more efficient or less efficient. So there are two key components here, measuring and comparing. Taking this analogy forward, suppose we have a building, say an apple, and you want to compare it with the rest of the apples. So you look at all of the buildings and say, okay, I know the size of my apple or the energy consumption of my building. and I go out and measure the energy consumption of all other buildings in the universe or in a region. Clearly, it's not feasible to measure the consumption of all buildings, so you select a subset and say, I'm going to select a subset and measure the comparison of my apple with the sample of apples. But when you do the subset, you would soon find that it's not only red apples, or there are many kinds of apples. There are red apples, green apples, blue apples, sorry, no blue apples, but who knows. So when you go out and measure, you would find that is it just okay to compare the size of the apple, because there are inherent variations in the apple or say in the buildings. So the first question is it okay to just go and compare the kilowatt hour per meter square per year of energy consumption across all the different kinds of apple? And that would get you thinking. If you continue to deliberate on the question, you would also realize that there are not only apples in the market. There are grapes and oranges and apples and guava and all sorts of fruits. So then you would know that just measuring the size of the apple with say size of grapes would not tell you that the larger apples are better than smaller grapes. This is not an apple-to-apple comparison. So that is what happens in our building situation also, that if you have the energy consumption of a building and you want to measure it, compare it with buildings of performance of other buildings, they are all very different types of buildings. So direct comparison of one value like kWh per meter square might not be the right choice. So when you go out and try to make this comparison, you'll find that there are just too many fruits in the sample in the market. And when people talk about energy efficiency or an efficient building, they might have apples in their mind and talking to somebody who has oranges in his or her mind. And then the comparison would not make sense. But still they would say, no, my building is more efficient because I use 20%, my EPI or the energy performance index is 20% lower than your energy performance index. And all the while they're talking about apples and oranges, but using the same metric to have the conversation. So the challenge before us is then how do we measure the performance of an apple and an orange? So this is the prime driver for energy benchmarking. Benchmarking benchmarks are a standard against which similar things can be measured and compared. So for cars we have liters, kilometer per liter. That's a benchmark, and then we say, okay, 2 cars, how many kilometer per liter do they give? And we say the benchmark is say 20 kilometer per liter, and then we say, okay, this car is giving lower mileage and a higher mileage, and we say this is efficient or inefficient. But in case of buildings, the buildings are very different. They have different uses. So you might have offices, hospitals, hotels, all different kinds of fruit. Within each building type, there might be different sizes. So within apples, there might be smaller apples because of genetic variation and larger apples. And just to say, just because an apple is large, does not mean it's performing better than a smaller apple, which might be more nutritious. Buildings operate for different times, different hours in a day. They have different number of users, number of workers in an office, or number of beds in the hospital, or number of rooms in a hotel, and so on. They may be located in different geographic regions, offer different level of comfort. So some might be totally conditioned, others might be partly conditioned, or maintaining different set point temperatures for that matter, and so on. So the difference between the buildings would be very large, and they would very soon start looking like a large basket of different assorted fruits. So some data was collected, and I'll actually come to the institutional part of this exercise a bit later on. And we found that on an average, the EPI, some of you might not be familiar, EPI is called the Energy Performance Index. It is the actual energy consumed by a building, normalized by per meter square of floor area. So kWh, kilowatt hour per meter square per year. So data was collected, and we found that hospitals on an average, so this notch here that you see shows you the average EPI of hospitals, was around 289 kilowatt hour per meter square, which was much higher than an actual average EPI of an office, which was almost like 172 kWh per meter square. So the variation in EPI between building types was very different and significantly different. So all these notches are non-overlapping and significantly different, which gives us a sense that the EPI is largely dependent on the building type. If we look deeper into it, we'll also find that maybe the ownership patterns have a different impact on the EPI of buildings. So just looking at offices, we found through data analysis that private office buildings EPI was significantly higher than public office buildings, almost on a ratio of 1:2. But then we said, why should this be the situation? Because we would like to think that private entities might be more concerned about energy use. So we thought maybe there are some parameters which are being overlooked. So we just sampled offices which were air conditioned, both conditioned private buildings and conditioned public buildings. And even after looking at conditioned public and conditioned private building, we found that EPI of conditioned public building was much lower than the EPI of private conditioned buildings. And this was also a ratio of 1:2 or more, and it was very confusing for us. In the next level, we normalized by the hours of operation, and we found that the average EPI of a public office building and a private office building was almost at par. So by this analysis, we found that it's not just the EPI, but you should look at many other parameters when you're comparing the EPI of two buildings. And here, just the hours of operation made so much of a difference. It so happens that the private offices were being operated for much longer hours in a day. So you need to normalize for building types, the hours of operation, the degree of conditioning, climate zone. However, all these normalizations are not linear. So in this example, we see that when we normalize kWh by building area, and this is case of hospitals, we found that they were more sensitive, the EPI was more sensitive to smaller hospitals than to larger hospitals. So if we did a mindless linear normalization just by area or by any of the parameters, we would still get a skewed number, skewed benchmark to compare two buildings. And again, in the case of climatic zones, we found that the to come with a more refined way to compare the performance of two buildings and then say that this building is more efficient than the other building. So again, Bureau of Energy Efficiency took the lead in this domain, and they started working from late 2008. And it was supported by the USAID-funded ECO3 project. And some data was collected under the ECO3 project and by ICMQ, which was hired by Bureau of Energy Efficiency. And finally, till end of 2011, and then the subsequent work which is happening right now under the project called Partnership to Advance Clean Energy. Connected. So and the subsequent work under the PACE-R project, which is Partnership to Advance Clean Energy, since 2012. So I would spend more time to explain the underlying methodology and the tool that was developed till 2011, and then kind of give an overview of what is happening since 2012 in this area, which is still a work in progress. So BEE along with ECO3 created a standardized data collection form, and then a few agencies were hired, primarily the ICMQ, and data was also contributed by many building owners and other agencies which had smaller number of data sets. All of that was compiled in a single database and the analysis was performed. The project was supported by ECO3. The data was collected from across the country, and for many building types, though the actual analysis happened for offices, hotels, and hospitals. These were the three large building types which had a much higher EPI than other types, of course, of the retail malls. So the objective was to come up with a rating scheme or a comparison scheme based on the actual performance of the building using contextual data rather than just the design intent. So the idea was, how can we say that the building is actually operating efficiently rather than saying the building was designed to operate efficiently. So this is the key difference from other intention-based codes or rating schemes, where in this case we are saying the performance evaluation would be based on the actual energy consumed. And at that time, the guiding principles were that we should look at the whole building level, use actual build energy data, provide a mechanism to compare against the peer groups. So it's just not saying that your building is efficient or not, but where do you stand in the whole spectrum of peer buildings, among peer buildings. And the scheme or the method should account for the operational characteristics of the building and not penalize for higher level of service or higher use intensity or amenities. And doing all of this, it should still be at the end of the day a very simple metric to evaluate and communicate building energy performance. So though at the back end there will be a relatively complex nonlinear model, but in the front end the model should still give you a very simple metric that people can use in their day-to-day communication among various stakeholders to talk about efficiency. So the model was formed, and it was based on statistical regression and distribution analysis. I would not go into the nitty-gritties of the model, but there's a paper on this model on ECO3's website. So it was a three-step process. In the first step, again I'll just quickly go through the methodology of actual model creation and then jump straight to the tool, which will be more interesting. In the first step, the average energy consumption was estimated based on different parameters of the building, like climate or person condition, space, built-up area, hours of operation, number of people working there, and so on. Then the actual energy consumption of the building was compared to the estimated energy consumption, and then said, okay, given these building characteristics, the building should have consumed 150 kWh per meter square, while it is consuming just 100 kWh per meter square. Therefore, it's 2/3 more efficient than an average building. And then this deviation from how far you are from an average consumption was used to give you a score. So if you are very far, if you are much less than an average building, you get a very high ranking. And if you are consuming much more than an average building, you get a very low ranking. If you are consuming around the average consumption, you get about a 50 percentile ranking. So this was the three main steps in the rating process. And then all that model was coded into a web-based tool, and I'll very quickly walk you through the tool environment. So on the top left side is where you would enter the building characteristics, and it's currently shown just as few building parameters like building area, energy, electricity consumed, and say some energy generated on site through DG, the climate zone, and the number of beds. So this is for hospitals. So once the user enters these building parameters, the model would calculate how much would be the EPI of a similar building. So in this case, the building's EPI was about 33 kWh per meter square, while a benchmark building would have consumed 328 kWh per meter square. So very close to the benchmark. So, but on the lower side. So the building is consuming a bit more energy than the benchmark. Then based on that, a rank was calculated saying this building rank is about 67 based on its peers. So what this means is that this building, 67% of the building stock is operating at a higher efficiency level than this building, and which is not a very good news for this building, that it's performing below average. The whole information can be visualized in a graphic form, where this red line is a kind of a DNA of the building, and the red dot is the building itself. So it shows you on the x-axis the rating it achieves, and on the y-axis the kilowatt hour per meter square. And on the second y-axis, the same building in blue is shown in kWh per bed. So sometimes the owners would want to know their performance in different metrics, and so therefore the tool was able to give you kWh per meter square or kWh per bed. Then based on that, a star label was computed, and in this case, because it is below than an average building, it just received 1 star, 5 star being the best, the highest rating. And then there was a table. So I'll walk you through the different components of this tool using different screenshots. So this is where you enter the data. This is where the star band is shown, and this is the graphic output. Now this building has an area of 7,000 meters square and consumes about, say, 25 lakh units, located in temperate zone, and has 200 beds. And the model then calculated it gets a rating of only 2 star, a rank of 40 percentile, and has an EPI of little less than 400 kWh per meter square. Now what if we changed the energy consumption of this building? So the figures in the red box is what we are going to change now. And suppose we had another building. Suppose we had the same building but consuming about half the energy. Then you would see that the red dot has moved down the curve. I'll go back and reduce the energy consumption. So the rank from 40 has improved to 5. So by reducing its energy consumption to about half, this building gets a performance rank of 5. That means only 5% of the building in the whole database is better than this building, and therefore this building gets a star rating of 4 star. But the red line is same. So this building's performance is defined by this red line, and the building just slides up and down this red line. However, if we change the building itself, so if we change the area and the number of beds, we'll find that the red line, take your eyes to this red line would move. Therefore, the new building would be evaluated on a very different performance curve. So if we change the area and the number of beds, you see the red line has shifted, and now this building performance rank is 12 and it gets 3 star rating. The tool also gives you, one more thing is that if you look at this bar chart here, the performance bands are also dynamic. So comparing this case with the previous case, you would see that the performance bands for 5 star, 4 star, 3 star, 2 star are also changing. So this is to say that even the bands in which these buildings fall are dynamic and determined by similar buildings, buildings having the same characteristics and same climate zone. Using that same tool, you can then set target levels. So say, okay, your building's EPI is 200 kWh per meter square, and currently it is having a rank of, say, 200 would be a 4 star or 5 star. And if you want to become 5 star, then you will have to reduce the EPI by 25 kWh per meter square. So you, as a designer, as a portfolio manager, you can set targets for all of your buildings, saying I want my buildings to be in this star category, and therefore this is the EPI that I should target. And mind it, these are dynamic EPIs, and therefore for all different kind of buildings or different sizes of buildings, you'll get a different band to be located in. So you just cannot say, I want EPI of all my office buildings to be more than 175, because this 175 EPI is only for one particular type of building, one particular type with a particular characteristic. So you should, rather than saying that I want my office building to be consuming energy less than 175 kWh per meter square, you should say I want my office building to be 5-star plus or 5-star. That is the best case. Because different office buildings in 5-star category may have different EPIs, but not the other way around. So this is again the whole tool, and this was a web-based tool. I'm saying was because for some reason the online interface is not working, but I have been told that they are fixing it and it will be up again in a couple of months. So 2-3 months is what I have been told. So that was the work done under the ECO3 project. Subsequent to being able to, in a very reasonable way, say what should be the average EPI of a building like a particular case, and where does your building stand in relation to that building and also in relation to the peers, you can then get a sense of how efficient your building is. So if the tool tells you that you're in top 5 percentile, then you are fairly confident that, okay, now the building was intended to be efficient and it's operating at this level, and the tool tells me that it's still in the top 5 percentile of the building stock, and I would consider that as efficient. Somebody else might say, okay, if it is in top 10 percentile, it is efficient. So efficiency then becomes a very relative term, and still the percentile ranks are comparable across different building types or subtypes also. So subsequent to that, we were posed with some other very interesting questions, and I'll very quickly walk you through that. So how do you know if your building is performing efficiently? So somebody walked to us and said, okay, this tool of yours tells us whether the building is efficient or not, but what if I just want to know whether it's performing efficiently or not, given that it has been designed well, but what if my operations team is not doing the right job? Somebody said, how can I know if the building is inefficient or it is just being operated inefficiently? So then the whole performance of the building was decomposed into 2 parts by this question. That there's a building itself which was designed and constructed efficiently, but it's being inefficiently operated. Or the other way, that, well, the building was not constructed or designed to be very efficient, but the operations team is doing a good job, and therefore there's no scope in improving the operations unless you do a major retrofit to the building itself. Then the third very important question was, if you are in a real estate transaction and you want to purchase a building, how would you know that you're actually purchasing an efficient building? So what it translates to us is, how can we have a benchmark which helps to answer or evaluate the performance of a building in a real estate deal, which would allow us to have some monetary value attached to energy efficiency. So if you can send a credible signal out there that the building you're purchasing is inherently efficient, independent of the way it is being operated, or has the potential to be very efficient if it is correctly operated, then you can possibly claim a higher premium on that property. So answering this question would then attach a real estate, a monetary value to energy efficiency in buildings. And I think that this would then actually push or create a market for energy efficient buildings in India. Some other questions were, how can I quickly identify saving potential in the buildings? I know that my building is efficient or inefficient, but where are the saving potentials? Is it in the operations? Is it in the asset? Is it in the lighting? Is it in air conditioning? So which part or component of the building is where the saving potentials lie? Now we can answer this question through a very detailed energy audit, but here the whole intention was how to very quickly is the operationalizing word here, identify where the savings are, and then decide whether it's worth going for an investment grade audit or not. And some follow-up questions were, how can government certify buildings as efficient? And then the policy question comes here whether they want to certify the building components and the design as efficient, or the whole building, including the building envelope and the systems and the way it is being operated. So you start looking at building as a whole, which is a sum of the physical building and the operation as one thing which can be certified, or it's just the building which is certified, and say, the tenants would change and the operations would change, but the building is efficient. So you can still claim to have a efficient stock, and operations may vary. And finally, how can the answers to some of these questions actually inform the design process itself? So we wanted to close the loop and say, okay, if we can answer some of these questions, then we can maybe perhaps inform the design process itself. And one of the way is that the clients can now come back and tell the designers, the architects and the engineers that I want the building so designed and constructed in a manner so that it's the asset, the building itself gets a higher rating irrespective of the operation. Or they can say, give me a building which is in top 5 percentile. So you enter into a realm of a performance-based contracting. So the answer to some of these questions were clubbed in three areas that we are now currently working on, and the project is called PACE-R, Partnership to Advance Clean Energy, and it's a research component of this project. There's a parallel deployment component also, but we are looking at benchmarking in the research component. And there are three themes that we are working on: improving the whole building benchmarking, which is looking at the building as a whole, the assets, the building assets, envelope systems, and the way it is being operated, all clubbed in one large metric. And second is decomposing the whole building into the assets and the operation. So how good are the assets given the way it is designed, constructed, specified? That gets a rating or a benchmark. And how it is being operated, so that gets a separate rating. And some kind of a mixture of the asset and operation determines the whole building benchmarking. So the asset benchmarking would be something like, independent of how the building is being operated, what rank can you give to the building? And the operation benchmarking would be, given this particular asset, how well it is being operated. And the last part is the system level benchmarking, which takes you more into the action oriented benchmarking, where you can not only benchmark the whole building or the assets and operations, but you can start benchmarking your lighting, your air conditioning, different systems within the building. So I'll quickly elaborate on each of these three themes that we are currently working on. In the whole building benchmarking, what the next step that we are taking is what we call the graduated approach. So you do a very simple benchmarking, just take 5-6 key parameters, and it's mainly designed to provide policy support and maybe relatively less accuracy, but the idea here is to promote more permeability so that we can have more and more buildings benchmarked. And by using a simple benchmarking, you would use much less information, maybe have a less accurate benchmark. But the benchmark, and this is suppose the scale of EPA, the benchmark would come with some kind of a confidence band, and you would know how far you are from the benchmark. Knowing well that because it's a simple benchmarking, it might have a confidence band which is this wide. So you would still know that your EPI is much higher than the benchmarking, the benchmark value. And if you are willing to provide more information into the tool, you might get into the realm of an advanced benchmarking, which will require more information. It can help you track performance. Would reduce the uncertainty band around the benchmark. So you move from a wider uncertainty band to a smaller uncertainty band when you go from a simple to an advanced benchmarking. So there's a trade-off between the resource need and the resource needed to get this benchmark correct and the accuracy of the benchmark itself. Under the second theme, when we say we are working on asset and operation performance, so the whole building might be divided into some components which are fixed over a long period of time, such as lighting, lighting controls, cooling system, wall insulation, orientation windows. So some of these things you cannot change. You cannot change the orientation of the building, or you would not change, say, insulation over a period of a decade or something like that. Whereas there are other things which are more on the operation sides, like plug loads, operating schedules, occupation behavior, maintenance, which can change, and as the users or the occupants change, all of these things would change. They can even change from season to season or year to year or day to day, depending on who the facility manager is. So then saying, instead of benchmarking the whole building like this, we can have one benchmark for the assets, which is shown in green color here, and one benchmark for the operations. And in this particular case, the red means they are poorly performing. So in this particular building is performing poorly on the operations and is good on the asset, whereas this building is, say, poor on the assets but is operated well. So taking this idea forward, suppose you have a scale of 0 to 100, with 0 being the best building, and you have a code or a label saying 25 percentile is the level beyond which something would be called compliant, or not compliant but would get a particular rating or a label. And then you ask your architects and designers to give you a building, and they design a building whose rank is, say, 20, which is higher than the code or the label requirement, and you're happy. But once you, so this is the asset rating that you do, but once you start the operation, you would find that the operational performance is much lower, leading to an overall rating which is below the code or the label requirement. And once you see this, then you can say, okay, I don't have to make any changes in the building assets. I just have to pull my operation up so that my overall building can go beyond the code or the label requirement. So that was the asset and the operation labeling. The third is the system level benchmarking. We have already seen this figure here. It's a very innovative way of showing what I'm going to talk about, what I've been talking about, showing the buildings as a jigsaw of different components. And here now each of the components have been given a benchmark. And in this case, we find that it's the cooling system which is the culprit, and whereas the lighting, control, and heating and orientation, they are all above the benchmark, so they are in green. And roof insulation, occupant behavior, and schedules are just on the average. So you start benchmarking individual components of the building, be it a component in the asset or component in the operation, and then say, okay, these are the two components where immediate attention is required. So in terms of, you can also benchmark the end users, so say lighting, heating, cooling, ventilation, and then you place your building's, say, a lighting requirement and say, okay, my lighting is in top 25 percentile. If your building's lighting is here, so you measure the performance of each of your end users and place it on a graph like that. This is for California, but we are working on something similar for the Indian buildings. And then you can place your building's lighting consumption on this spectrum and say where you stand. Or you can just look at your whole building like this and say a typical building's energy consumption is like this, a good practice is like this, and this is where you are. And then say, okay, which are the areas where you want to make more focused intervention. This takes the same idea forward and gets into, suppose you get a lighting benchmarking and you find that the average, the benchmark value for lighting is 27 and you're consuming 52 kilowatt hour per meter square. So this information by itself doesn't help you much to take any further action, rather than just saying that, okay, there's some problem with the lighting because my lighting consumption is almost twice as my benchmark value. So what you do for an action level information is say, okay, my lighting consumption is a function of the installed load and the effective hours that the light are being used. The installed load is a function of the lighting level and the efficiency, whereas effective hours is a function of how many hours the building is occupied plus some kind of a control and a management factor. And then you see in each of this how good or bad you are with respect to the benchmark. And then you say, okay, I am really bad in the efficiency because I don't want to do anything with my occupied hours. These are my business decisions, and I cannot shut my building. So the efficiency and the controls is where the maximum saving potential lie. And these are the two things that I would work on. And the whole information can also be seen as
It seems that we have some networking issue. Just let us try to find out what's the problem.
okay. I think the connection was lost for a few minutes. I was just trying to elaborate on the screen. I'll move ahead so that we can have some Q&As at the end of it. So just to summarize, we are working on whole building, asset operation, and system levels. In the whole building, we are working on the basic and the detailed model. At the system levels, we are working on the end users and the components. So not only benchmarking the end users, but also the components. And some of the uses of these three approach is that it can help you to do performance evaluation, identify best practices, incentivize performance, set design targets, rating certifications, saving estimation, and a whole list of all these things would be the potential use of these three strategies. And it can be deployed through government, through BE, through institutions and organizations, and through private sector. So I'll say that by doing all of this, we can extend the idea of comparing and evaluating further to improving operations, retrofit, and learning, and finally help in improving the targets that we set for ourselves at the design stage. So I'll stop here and open the house for questions.